So this next topic, we're going to talk specifically about a term called heat. And we know that matter changes phases, and when matter changes phases, it requires the exchange of energy. That energy is specifically referred to as heat. So heat is the amount of stored energy by the temperature and phase of matter. So it's not just the temperature of the system, it's also the phase that those particles are currently in. So a cold solid would have a low amount of heat, but it has some heat, and a really high temperature gas has a lot of heat because it's at a higher phase and a higher temperature. Okay, the symbol that we use to associate with heat is a capital Q, and the unit for heat is always measured in joules. One of the things we're going to talk about is the exchange of heat from one system to the other. And so if we have a system that has a high amount of energy and the particles are moving really fast, and we put it in contact with a low energy system where the particles are moving really slow, the faster moving particles are going to slam into the slower moving particles more often, transferring their energy. So energy is always a flow, and it flows from the particles with higher energy to the particles with lower energy. So the easy way to remember that is that heat always flows from hot to cold. It's easier for the hot system with more energy to transfer through collisions its energy to the colder system. Now there's a huge distinction between these next two terms. Temperature is the average kinetic or motion energy particles have in a system. Okay? Heat is the transfer of kinetic energy of those particles. So you can take your body temperature, you stick a thermometer under your tongue, that's your current state. It's not how much is being exchanged. Heat is how much is actually being exchanged from you to your surroundings or your surroundings to you. So temperature is a measurement, heat is a change, right? So when we add heat or when we release heat, we used these two terms before. Endothermic, that prefix endo means that heat enters, and exothermic, that prefix exo means that heat exits. So if I add a bunch of energy to a system, I'm heating it up by adding that energy. So a heating curve is the graphical process in which heat flows into a system. And if heat is leaving, then that means that it's losing energy and cooling down. So a cooling curve is the graphical process in which heat flows out of a system. So the two graphs off to the right show the generic pattern of a heating curve and a cooling curve. And the one thing I'll point out is that all curves that we're going to talk about always have to have 1, 2, 3, 4, 5 segments. 3 diagonal segments for each phase, and then 2 plateaus to showcase that change between the 2 phases. Okay? So you can't go in there if you're drawing a graph on a quiz or a test or a lab and just do a zigzag up and down. There is an intentional number of segments. So for a heating curve, we're going to, over time, add heat, which will cause our temperature to go up. And at the lowest temperature, no heat added, we've got a solid. And then we're going to melt that solid into a liquid. And then we're going to heat up that liquid to the point where that particular temperature causes the liquid to evaporate into a gas. Okay? The opposite process for a cooling curve, again, over time, would be removing heat. But now we start at a higher temperature and we work our way to a colder temperature. So at the highest possible temperature, this time we start as a gas and we condense that gas at this particular temperature down to a liquid. We cool that liquid down so that the particles start slowing down and come closer together, and then the additional removal of heat freezes those liquid particles into a particular pattern, and that fixed pattern is now the solid state. Okay, so there is a certain energy associated with the temperature change and with the phase change because we're always moving in the x direction, left or right. There's just a couple of times in the y value where we plateau and stay constant, and that's when we're changing the phase. So other than looking at these two graphs, there's another way that we're going to show a representation of that energy exchange, and we use what's called an LOL chart. Right? So it's not LOL because they're so great, they're going to make you laugh out loud. All right? The LOL chart is a way for us to graphically illustrate the energy stored for our system in the two ways that we talked about. Thermally, based on temperature, and the phase energy based on the arrangement. So a generic LOL chart looks like this, which is why we call it an LOL chart. The basic idea is that this is your initial input, and this is your final input based on the information that you're provided, and then the O is your system. So this is the beginning, this is what we're evaluating, and this is the end. And once you see a couple of examples, it's a pretty straightforward exercise. So in terms of thermal energy, that's the energy stored by the speed of particles, and that's directly related to the temperature. Okay, the symbol that we use is capital E with a subscript TH for thermal, and the change means that particles are going to be moving either faster or slower. Again, we have to speed up solid particles to a certain temperature in order for them to melt, and then we have to speed up liquid particles to a certain temperature for them to evaporate, and the opposite holds true. So when we look at this L, under our thermal energy column, think of this as like a bar graph. A cold temperature is a low amount of thermal energy. So for cold, we're going to say this maybe fills up just 1 bar of thermal energy. For something that's at room temperature, which is slightly warmer, we might say that it fills up 2 bars for thermal energy. Okay, and we're talking in general terms. There's not like a specific number associated with 1 bar or 2 bars. And then if something is particularly hot, we might fill it all the way up to the highest possible thermal energy, which is 4 bars. Okay? Now, when we talk about a system changing phase, that's the energy change stored due to the arrangement of the particles. And just like thermal, we've got a symbol for it. It's another capital E. This time it's subscript PH for phase. And this change causes particles to move closer together or farther apart. Think in terms of when you freeze a liquid into a solid. They're freezing closer together in that particular close packed arrangement. So solids, because they're so confined into one particular spot, have low phase energy. So under the phase energy column for a solid, we're only going to put 1 bar. For a liquid, we're going to put 2 bars. And because gases have such a larger freedom of mobility, this one is very specific. Gases always have to go up to the maximum amount, 4 bars. Okay. So solids always represent 1 phase energy, liquids 2 phase energy, gases 4. The thermal energy, the temperature of the system, we could use 1, 2, 3, or 4. It depends on if it's room temperature, warm, hot. Again, it's relative based on the system that we're trying to evaluate. You probably noticed that there's a third energy column. We're going to ignore that third energy column going forward. That stands for the chemical energy. We're not going to be factoring in how the chemical energy change of a reaction might affect the system. So that'll be there, we just won't use it. So again, an energy bar chart or an LOL chart is a visual of phase and thermal energy change. The system, which is that O, is the part of the universe or the experiment that you are studying. So the LOL location is inside the O. Surroundings is everything else. So one of the important things that we're also going to be looking at is how our surroundings and the energy that's being transferred back and forth affect the system. So the LOL location is outside the O. Okay? So it's important to remember that temperature is constant on a phase change graph. The reason that I bring this up again, especially in terms of the surroundings, is that an LOL chart, when we get through these examples, can only illustrate one type of change. So either the energy from our surroundings is coming in to warm up or cool down our system, or the energy coming in or going out is changing the phase energy of our system. Okay, so for this first example, it says complete an LOL chart for heating water. It doesn't say anything about the water boiling or any other change other than the fact that it's heating up, so it's warming up. So the first thing we'd fill in inside the circle is that our system that we're looking at is this sample of water. And if the water isn't being told that it's changing a phase, initially it gets 2 bars of liquid phase energy, and finally it stayed a liquid. It didn't change. Okay, so our liquid phase didn't change. In terms of our energy diagram, we're in this segment here where we're a liquid from beginning to end. So this is the segment that we're in. We're constantly a liquid phase. So what is changing from here to here if you're a liquid at the beginning and a liquid at the end? The temperature's changing. Okay, so again, an LOL chart can only illustrate one type of change. So for heating water, we have to start with maybe cold water and then warm that up to 2 bars. So does this satisfy the thermal energy increasing, showing water's heating up? Yeah. Is this the only answer? No. Okay, we could have started with room temperature water and heated it up to a warmer temperature. Okay, there's multiple answers that can satisfy these questions, but you and your LOL chart need to be able to show that particular change that the question is referring to. The last thing is we need to be able to illustrate, did the energy endothermically enter into the system or did it exothermically exit the system? And the one nice thing about the LOL chart is that the total amount of energy is either increasing or decreasing to illustrate that point. So in this example here, I've got 1, 2, 3, 4 total bars of energy. And on the right side, I've got 5 total bars of energy. So that means that energy had to have gone into the system to increase from 4 to 5. And we're specifically going to put the number of bars that from the outside went into the system. So it gained 1 bar of energy. Okay? So in the last example, it says complete an LOL chart for freezing liquid water into solid water. So again, our system is a sample of water. This time we're starting from a liquid phase and we're ending at a solid phase. So that keyword freezing only shows up here on a cooling curve, which is an exothermic process. So we're taking energy out of this system. And if we're freezing from here to here, from the liquid phase turning into the solid phase, the one thing that stays constant is temperature. So in order for the energy being pulled out of this system to freeze this liquid into a solid, this water has to be cold. Even though it doesn't say anything about cold water freezing, right? You can't take hot water, put it in the freezer, and then expect it to instantaneously freeze. You'd have to cool the hot water down first, which would require another LOL chart. And then once that water is cooled down, then we can freeze it into the solid phase. But because temperature has to remain constant, our thermal energy starts cold, ends cold, but the energy that's leaving the system is enough to cause it to go from that liquid phase to the solid phase. Again, here we've got 3 total bars. Now we've only got 2 bars. So 1 bar of energy is exiting from the system.